off with a question or?
I can go.
Sure.
Could you work through a problem with a mass on an inclined plane? And like we have to find like the acceleration and maybe like and solve a kinematics equation.
Sure.
Right. Because I'm confused on like what we're finding when we use sine and cosine with the angle and with the mass.
Okay. Yeah, there are several examples in the stuff that I sent out to you or put on the website, but we can probably make one up. So let's suppose, remember on this upcoming exam, we're not going to use the laws of kinetic and static friction. There was one example in, I think, maybe an old exam or something where you were given the magnitude of the friction force. That's okay, because you don't really need to know anything about friction other than when two surfaces are sliding, that it always opposes the direction of the sliding against the surface. But let's do a frictionless problem here. We'll make, easy angle, 30 degrees, frictionless inclined plane, and we've got a 5 kilogram mass on it. And let's suppose that well, how about this? I give it an initial shove up the plane direction. So I shove it, it starts going up the plane at, 5 meters per second. Well, it's going to slow down, right? Because it's going up against gravity. So as it slows down, it will eventually come to rest and come back down and pass where it was before, right? So we're going to say, I release it at 5 meters per second. And my question is going to be, how much time does it take to go up and come back and pass by the point at which I released it at 5 meters per second, right? I don't know that I'm going to write that down in words, but that's a perfectly well-defined problem. And our goal first is, as always, to find the acceleration. I need to know how fast this thing is going to accelerate. It's moving in one dimension, happens to be a tilted dimension. But to find acceleration, we're going to use F net equals ma. And to do F net equals ma, we need a free body diagram. So I'm going to just draw my blob. On inclined planes, I tend to draw them tilted. And we need to figure out all the forces on it. And of course, there's a gravitational force of magnitude mg, 5 times 9.8 in SI units. And if that were the only force, it would be in free fall. So that can't be true. There's got to be a force from the plane. And since it's frictionless, that force is in the direction perpendicular to the surface. And traditionally, people call that a normal force. Normal means perpendicular. So, and I can't think of any other, there's no friction forces, so there's no force parallel to the plane. And that seems like all the forces that are there. So let's now, as always, attach a set of axes. And in these free body diagrams, the rule of thumb is always, if you know the direction that something is accelerating, put one of your axes in that direction. That's going to save you work. Sometimes, you may not even be able to finish it if you can't do that. But so let's take my plus x axis. I'm taking it down the plane only because I know the acceleration is going to be in the direction that its velocity is trending down the plane. And so that will make at least a positive acceleration. Plus y going perpendicular to the plane. And then we want the x acceleration, so I can do that kinematics problem. Okay, so why not just go for it? And we'll find out going for it pays off here. We will only need the x F net equals ma equation. Later on, when we throw in the friction laws, we'll need the y one too. But for right now, since I know AY is 0, I don't need to know anything. It's not accelerating in that direction. All the acceleration is along the line it's going. So AX is what I'm going for, at least in the short term. Sum of the force X components equals MAX. The normal force has 0 X component. It's all along Y. Going from tail to tip, you don't need to go along X at all. It's just along Y. So the only one that has a non-zero X component is the weight force. And remember, the meaning of the X and Y components is you start at the tail and you go along X or along Y and then just along the other one, right? So I'm going to say, let's draw first going just along Y and then going just along X to get to the tip. And that always draws out a right triangle for which you can, this is essentially what Nafis is asking about. I know the hypotenuse has length mg, 5 times 9.8, and I want to find the X component. In my coordinate system, is the X component of this weight force positive or negative? It's positive because in going from the tail to the tip, I have to move along the positive X direction. So yeah, I don't need to put a plus sign in there, but just to remind myself that I've thought about it. And then what goes next to it is just the length of that side. Lengths are always positive. So if you want a component, you got to put in the extra plus or minus yourself. But in this case, it just comes to nothing there. Okay, so I know the hypotenuse. If I only knew one angle in this right triangle besides the right angle, I'd be done. And after you do a few of these problems, you'll sort of get the idea of how to just write it in. And the idea is, if you draw a line perpendicular to the plane coming out of your mass, and you draw a line going straight down, that's going to be the direction of the weight vector. This angle here is always going to be the same as the angle of the incline to the horizontal. And, typically that's what I give. If someone were feeling really weird, they might give you this angle up here. You could immediately figure out what that one is down there. So if it's a 30-degree inclined plane, this angle is 30 degrees. Why? Well, this is a right triangle here. And so these two have to add up to 90. So this one's 60 here. But this is also a right angle right there. So these two have to add up to 90. And if this one's 60, this one's 30. Once you prove that to yourself, then you'll start getting used to just saying, oh, I know, there's an angle I know right away. And that's a useful angle because that's this angle here. Same one in that little right triangle there, right? We're essentially drawing this out like that. Okay, so the X component, that's the length of this side. My way of doing it is you take from the hypotenuse, I'm going across the angle that I know. So I use the sine because I don't like going across the angle and I don't like the sine. 5 times 9.8, you start with the hypotenuse and then multiply by the sine of the angle if you're going across it. And again, you can use SOHCAHTOA. The other one's X component was 0. So that's the only non-zero X component. That's equal to the mass of the thing in the free body diagram times AX, and AX is what I want here. So I didn't bring my calculator, I apologize, but some of you can calculate what 9.8 times the sine of 30. Let's see. Sine of 30 is 1/2, right? So that's 4.9, I think. Isn't that right? That's what I get for choosing really nice numbers in my made up example. Tell me if I'm wrong there. Sine of 30, I think, is 1/2. Yeah. Okay, so that's big. We're going to need that for all kinds of problems that might have a follow-on, any sort of kinematics kind of thing. And now my thing was, here's the initial condition. This thing slides up and then comes back. And at the moment it sits again in this, it doesn't sit there, but it's passing by that location on the way down. How much time between when I released it and when it passes there on the way down? I don't want to write that out in words, but that's what I'm making out. So Initial is going to be just after release it. Final is passing by that location again. Who wants to tell me a kinematics equation that might help there? Yes. Okay, so you're talking about the one with the squares in it? Yeah, okay, so that's Vx final squared equals Vx initial squared plus 2ax delta x. Okay, so if I take initial to be just after I release it and final to be when it's passing that position on the way down, what's delta x? 0. Well, that makes this into kind of not so interesting of an equation, right? If this is 0, because now I could have chosen a different initial and final, but it's not so clear since I want the time between initial and final. That one is just saying that the speed as it passes by on the way down is the same magnitude of the speed it left with. In other words, if I push it up, there's no friction. This wouldn't be true with friction, right? Friction would kind of slow it down, it would be going slower on the way back down. But if I push it at 5 meters per second on the way up, when it comes by that place on the way down, it's going to be moving at 5 meters per second. All that will change is the sign. Vx is equal to plus or minus Vx0. And we know it's negative if the first one, actually, the upward one would be negative and the other one would be positive. Yeah. Delta x is 0 because I'm pushing this thing. Let's say we're keeping track of the front edge of this, right? So it goes up. Let's assume we have enough plane that it doesn't run out of inclined plane. It goes up, comes momentarily to rest, and then starts accelerating down. Started here, ended here. I didn't even specify what x is, but I know if this is at x equals -3, when it's passing by that on the way down, it's going to be at x equals -3, whatever point on the box I'm keeping track of for its coordinate. So that doesn't seem so helpful. What about the other two equations? They involve t's. Yeah, so. Well, there are two. Oh, you're saying the one with just velocity and time? Yeah, okay, so let's try that one. Vx final is equal to Vx initial plus ax times t. Okay, so same initial and final I described before. So that's the t I want. Okay. What is Vx final positive or negative in my coordinate system? Yeah, on the way back down, isn't it going this way? And that's in my positive chosen direction, right? So Vx final, we already did the work, but you know, a lot of people have this intuition, right? Frictionless thing, it's just like when you throw something up at 3 meters per second, when it passes that same point of release on the way down, it will be moving at 3 meters per second in the other direction if it moves with constant acceleration. In other words, if air resistance is negligible. So in this case, Vx final is going to be +5. I've got too many 5s in this problem, but 5 meters per second, right? It's going to be positive because it's moving in my positive x direction. What's Vx initial? No, it's just after I released it. How fast? What was its x component? -5. Ax is positive in this case, right? It's accelerating in the direction down the plane, 4.9 times t. So I add that over there. That gives me a 10 divided by 4.9 is t in seconds. So be very close to 2 seconds. We could have gotten it from the other one too. You know, you sort of, when you watch someone do this on the board, you think, wow, would I know? I wouldn't have chosen that one. I would have chosen this one, x equals x initial plus Vx initial times t plus 1/2 ax t squared. Let's see what comes out of there. Let's suppose we call the point, you know, I put the origin of the coordinate system at wherever I'm marking my points from on the box, right? So it starts out at x equals 0 and it ends up at x equals 0. Vx0 is -5, right? T plus AX is 4.9, so we have 4.9 over 2 times T squared, and I've got to solve that equation. And anytime you don't have one of, if you have a t squared plus bt plus c, if you have any one of those terms missing, you don't have to use the quadratic formula. Here I'm missing the constant term, right? The constant term is 0. So I can solve this without using the quadratic formula by just factoring, right? I could say common factor of t in both of these, factor it out. I have a -5 plus 4.9 over 2t. And then that fact, I hope you remember from high school algebra, your freshman year, whenever that was, product of two things equaling 0. The only way that can happen is if one of them is 0. Two non-zero things multiply together to give 0. That just doesn't happen. So then I say either t equals 0 or -5 plus 4.9 over 2t equals 0. And that would allow me to solve for t. And notice when I solve this equation, I'll get exactly the same thing I would have gotten up there, right? When I double, multiply by 2, I'll get a 10, and then I'll divide by 4.9, just like I would have up there. So it's not, I would say if you knew this, that it goes up at 5, it comes back down at 5 when it passes the same place. This one looks a little bit easier, but it's not too bad. At least we didn't have to use the quadratic.
Dr. Kelly,
Yeah.
If it comes back down at 5, then why would that be its initial why would its initial velocity be -5?
It's only a peculiarity of the fact that I chose the plus x axis to be going down the plane. So when in this problem, my verbal description is I give it a push up the plane. So it initially has a velocity in the negative x direction. That's a negative x component for velocity initial. Finally, when it's passing that point on the way down, then it's moving in the positive x direction. So Vx final is positive, but Vx initial is negative. Had I chosen my axes, there's nothing wrong with choosing plus x in that direction. A lot of things would have switched signs, but in the end, the things we calculate would have been the same. Ax would have then been -4.9, right? But the amount of time should still be the same. Okay, good question, Nafis. Who else wants to?
One more question?
Yeah.
How did you, your first step was putting a plus in front of the force, like Fx. Can you explain how you knew it was going to be a positive force again?
Yes. Then this is easy to forget. And sometimes, teachers don't emphasize it enough, but here's how I explain it. What does a component mean? If I have a vector like this, I just say, here we are floating in the middle of space, nothing for context. What are the x and y components of this vector? There's no sensible answer to that because there aren't any real x and y axes in the world. They're things that you make up. So either they have to be given to you or you have to choose them. So, I would say, if I chose my axes to look like this, x going to the right and y going up, then the way to think about the signs of the components is in going from the tail to the tip of the vector, right? Going from the tail to the arrowhead. I go all along x until I get to the point where all I have to do is move along y to get up to the tip of the vector. And the lengths of those two sides of that right triangle are the magnitudes of the components. I've still got to put in the signs myself, but I can see the sign is if I move in the plus x direction in going from the tail to the tip, that's a positive x component. If I move in the plus y direction, that's a positive y component. Now, let me change my mind here. I'm going to say, let's choose my plus x going up that way. And I know I'm getting to the edge of what you can probably see here, Nafis, because I've drawn a line on the board. Plus y going down this way, plus x going in that direction. In going from tail to tip, this isn't the correct right triangle I want to draw, right? And going from tail to tip, I want to maybe first go along X. That means parallel to the X-axis until I get to the point where all I have to do is move parallel to Y and it will send me to the tip. And that draws the right triangle I'm interested in. So in this case, in going from tail to tip, I moved along the plus X direction, but then along the minus Y direction. So my first step would be to say, Vx is positive something. Vy is negative something. And then all I got to do is figure out the lengths of these two sides of the right triangle. You know, if this speed it's moving at is 3 meters per second, and I knew an angle in there or something like that, I could figure out the lengths of the side. But lengths of sides are always positive numbers, right? Components need not be positive, so you've got to put in the correct sign along with it, or, you know, and I always do that by saying, in going from the tail to the tip, positive X direction, negative Y direction, or you can go this way, negative Y direction, positive X direction. And as you do that, you'll trace out a right triangle.
Okay, yeah, that clears it up.
Okay, good. Other questions? Yeah. Sure, sure. There was an example in something. Right, or what I was thinking of was, it was actually in the problems, I think, that you were given for lab. There's nothing wrong with that number 2, and we can talk about that one if you want. It gives you, if I remember correctly, a position graph, and you have to draw the velocity graph, right? But if you have a velocity graph, it's even better practice to try to draw the position and the acceleration, because you kind of have to think in 2 different directions, and that's stuff we did in lab. And for me, you can see it's appearing in some of this review and old exam stuff. So that means you bump that way up in terms of likelihood, and you're studying priority, right? Know how to do those kinds of things. Of course, you got to know how to do these projectile motion kinds of problems, one-dimensional kinematics, incline, you know, you could pretty much write down a lot of the high likelihood problems. Inclined planes, I like those because, you know, it's one of the only cases where you have to use kind of tilted axes that we've done so far. We'll see more complicated examples later on, but it's the first non-trivial kind of, I really have to break things up into X and Y components and think about them. Okay, so I'm going to draw the one that we did in the lab, or try my best to draw it. All of these things, we're trying to get something that's qualitatively correct. That means it's not obviously wrong, since they're, you know, often I don't label the axes on it. It's impossible to get numbers off, but you want something that qualitatively is doing the correct thing. So I'm looking in the stuff that you did in lab last week, the extra problems that were at the end. So let's draw some axes. Here is Vx as a function of time. Here is x as a function of time, and here's ax as a function of time. And we were given the following velocity graph. At every value, it was positive. Okay, so let me just roughly say, here's 1, 2, 3, 4, and 5. Looks like there's marked in seconds. And if we need it later on, this velocity is given in meters per second. I don't know that I'll be able to draw it faithfully enough, but it goes up linearly to a height of 2 meters per second. And then it looks like there's some sort of parabola piece that just barely hits the axis and comes back up to exactly the same height there. And then after that, it stays constant from 3 seconds to 5 seconds. Okay. So let's do the easy case first. We know, or at least we said in class, and this is something hopefully you practiced in your lab section, the slope of the velocity versus time graph is equal to the value of the acceleration at that time. So I just have to do that time after time after time and build up a graph down here. Okay, given that the slope of this graph corresponds to the value on this graph, if I go back to t equals 0, where's the first point I'm going to put on this graph? Should I put it at a positive, negative, or 0 value? If I just want to put the first point on there. Well, so the words I just said are you need to take the slope of the tangent line up here, and that tells me the value or the height of this graph there. So it looks positive. I mean, it's a little bit ambiguous because it's right where the graph ends. Let's pretend it keeps going in that direction. So it's unambiguous. Slope of the tangent, right? This is a positive slope. This is 0 slope. These are negative slopes. I'm hoping everybody's okay with that. And so this is a pretty positive slope. And so I'm going to start off at a pretty positive height. And all the way through 1 second, the slope of a tangent line I could attach. Tell me if this isn't resonating with, words that you know. Slope of the tangent line is the same all the way until 1 second. And so the height of this curve is the same. Slope of the tangent line corresponds to heights. Positive slopes means a positive height of the curve. Negative slopes means a negative height of the curve. Okay, then all of a sudden everything changes. The slope of the tangent line suddenly becomes really negative. That means the height of this curve suddenly becomes really negative. I don't know how far down to go because the axes weren't even labeled on the other graph, but I just want to be sort of qualitatively correct. It looks like it's more negative than this one is positive, right? If they were sort of equal angles to the vertical or to the horizontal, but this one should be down a little bit further. And then how should that graph, somebody help me continue. What's the trend as we go in this direction? How should I continue from this point to the right? Yeah. Yeah, it's becoming less negative. Slope of the tangent line was very negative, but then it progresses to less and less and less negative. By 2, it reaches 0. So let's put 2 down here. The height of this curve then becomes less and less and less negative, and by 2, it becomes 0. Now, should I put a little curve in there? It's hard to say, but at least it's not obviously wrong, right? It has the right trend there. So it started very negative slope, heading to 0 slope. Very negative height, heading to 0 height. And, if you know something about calculus, this is a quadratic function. When you take a derivative of a quadratic function, you get a linear function, and that's how things go from position to velocity, the acceleration. But here we're just talking about slopes of tangent lines. Okay, after 2, it's a little bit positive, more positive, slope of the tangent line, more positive, more positive. Height becomes a little bit positive, more positive, more positive, more positive, and reaches a maximum height at 3, where the slope of the tangent line is maximum and positive. After that, slope of the tangent line suddenly goes to 0, flat line. So here, the height of this curve suddenly jumps down to 0 for the rest of the time that's shown. Okay, so that's one direction. That's sort of going down, going from velocity to acceleration. If you were given position as you were in that sample exam and you were asked to give velocity, it would be the same thing, right? Slope of the tangent line up here gives the height down there. Yeah. Somebody else help me explain why this is down at a height of 0 rather than a height of 2 on this graph. Yes. Right, but just in terms of slopes of tangent lines, what you said is totally correct, but I'm just throwing intuition out the window and saying I'm just going to mechanically turn it into this. So yeah, the slope, I'm attaching a tangent line. here and here and here. Slope is 0, slope is 0, slope is 0. Height is 0, height is 0, height is 0, height is 0. The slope above goes to the height down below, at least the way I'm drawing it with position, velocity, acceleration. Other questions on that part? Okay, now let's go the other direction. This requires maybe a little bit more thought, but we're going to use the same fact. Slope of the tangent line up here gives me the height of the curve down here. Now this curve happens to start out at a height of 0. What does that tell me I should do right at the beginning of the graph up here that I'm about to start drawing? When I'm drawing it right near 0, what should I be doing? I mean, t equals 0, right? What I'm saying. I just want to put the first little bit of the graph near t equals 0. Should I be, well, here's something I always ask my lab. Should I start positive, negative, or 0 value there? What do you think? Negative, what are you looking at for the negative? Is it the negative value down here? Yeah, so the answer is I don't know. And there's no correct answer for that because all I know is the height of the curve is 0. And all that tells me about is the slope of the tangent line. Slope of the tangent line should be 0 right at t equals 0. Well, that could be true here or up here or up here. There are lots of ways to be 0 slope of the tangent line. Another way to think of it is this is telling me my velocity as a function of time. And if that's all I know, I don't know when I started whether I was near the origin on the x-axis or I was near x equals 1,000 meters. I could have had that same velocity as a function of time at both locations. So it doesn't tell me anything about when you go up. And if you're a calculus person, you may remember this is differentiation, this is integration. You have that annoying plus c and you don't know what the c is. Like, so that's telling us that whatever graph I draw up here, if I just move it up, that's also another correct graph. Now, that doesn't mean there's not a good choice. Given that this height is always positive, or at least never becomes negative over here, right? This graph is always positive. Do you think I should start up high in the positive, down low in the negative, or close to 0? Yeah, I want to go on the negative side because since this height is positive, that means the slope of the tangent line of the curve I'm going to be drawing is always positive, and that means it's just going to be going up and up and up and up and up. And if I start near the top of the axes, I'm just going to go off the top, and that's going to be inconvenient. So I'm going to choose to start my graph just for my own convenience down here. And we're looking at this. Height down here is the slope of the tangent line up here. Height is 0, so the slope of the tangent line starts out at 0. That means I should be going horizontally there, right? But it doesn't stay at 0, right? Then the height becomes a little bit positive, a little bit more positive, a little bit more positive. So the slope of the tangent line becomes a little bit positive, a little bit more positive, a little bit more positive, until we reach this point right here. The height has reached its maximum value. I mean, that means the slope of the tangent line has reached its maximum value. So it just keeps getting steeper and steeper and steeper until we reach that point. Slope of the tangent line is getting bigger, more and more and more positive because the height was getting more and more positive there. All right. Then the slope of the, the height of this curve starts becoming less positive, less positive, less positive, and reaches a value of 0 at 2. That means the slope of the tangent line, which was quite positive, starts becoming less and less positive. That means instead of going so steeply, it's sort of, going off, and it should reach the top of a hill at 2, because the height being 0 here means the slope of the tangent line is going all the way down to 0 there. Okay. After that point, slope of the tangent line was 0, but then it starts becoming positive again and keeps getting more positive until 3. So starts out at 0, becomes more and more and more positive until we hit 3. I didn't do the best job of drawing it right there, but it's supposed to be nice and smooth, like just snaking through 2 and just barely becoming horizontal and then going up. And then what happens after 3? Yeah, whatever height I was at when I approached 3, whatever height I was at, that means whatever slope of the tangent line I was at, I've got to keep that slope of the tangent line forevermore, right? Because the height stayed the same forevermore down here. So the slope of the tangent line, whatever it is, it just keeps going along a line up in that direction. I ran out of space on the top, but that's kind of the idea there. Any other worries or examples of this type before we move on to something else? Okay. Someone want to suggest another problem or type? Sarah? Sure. I don't think I brought my homework, and so if it's easy enough to tell me, I can try to draw it up here. Okay. Okay, so you got a 2, a 9, and a 6. Frictionless surface, I assume. So 3 blocks butted up against each other, 2 kilograms, 9 kilograms, 6 kilograms. Okay, and then there are some forces on the left and the right. So someone's pushing like this over here, is that right? And what's that for you? 13 newtons, and then someone's pushing from this side, 8 newtons. Okay. And what's the first question that we have to answer?
What is the magnitude of the force exerted on the block with 9 kilograms by the block with 9?
Okay, so we want the magnitude of the force on the 9 by the 6. Could write it that way, right? So if I could find the x component of that force, I haven't chosen an x-axis yet, but if I did find the x component, I would just throw away any minus signs. When someone says, what's the magnitude of the force? You just, if there's a minus sign, because it's going to be along the x direction, right? These, I'm assuming these blocks are totally, sitting down on the plane, and all the pushing is to the left and to the right. Okay, and it looks like I could kind of figure that out already, at least the sign, It looks like since you're pushing with a greater force on this side than on this side, it's going to start accelerating in that direction to the right, right? Maybe I'll call, because of that reason, I slightly prefer plus x along the direction of acceleration rather than opposite. And then when I solve in my coordinate system for the x component, am I going to expect this to be positive or negative? Of course, I'm going to throw away the minus sign at the end because we just want the magnitude of the force. But now that I'm going to solve for a component first. In my component, is the 6 force on the 9 going to have a positive or negative x component? It's going to be negative, right? The 9 is going to be pushing on the 6 in that direction. So the 6 has got to be pushing on the, if you're butted up against a box in front of you and you're accelerating, you're going to feel that box pushing back on you in that direction. Okay, so that's what we're going to sort of go for first. All right, anybody have an idea of how we might begin this problem? I don't know why I erased that. I don't want to forget. F on 9 by 6 equals what? Anybody have an idea of what to do first? Find a what? Find the acceleration. Okay, how could I find the acceleration? Yeah, the easiest thing to do, and this is like the one where we had things attached by strings, but we also had one where objects were bunched together. And The reason is, since these are all, they have the same velocity at any time, all three of them. So there's only one acceleration, right? And I could think about this object's acceleration, but it's going to be the same as this one, or all three of them together. So let me, at least at first, to find the acceleration, lump them all together. So that's 6 and 9 is 15, 17 kilograms. So let's do a free body diagram for that whole mess. I'm going to put a 17 there just to remind myself of what it means. Okay. What forces are reaching in from the outside? Remember, we don't need forces inside that thing. I don't need to include the force of the 2 on the 9 because that's in the middle of this. But what I want is forces reaching in from the outside and pulling or pushing, whether they're contact forces or action at a distance kind of forces. So the 13 is certainly pushing to the right? So I would say there's a 13 Newton in that direction. The 8 is reaching in from the outside and pushing to the left. So there's an 8 Newton force in that direction. There's got to be a normal force. There's no friction in this problem, so I don't need to worry about a friction force. And there's a weight force. 17 times 9.8. So that would be my free body diagram. And I'm not actually going to really use the vertical direction, but I'm going to stick with my choice of x-axis going to the right. You could take plus y up if you want. And then the whole point of doing this is sum of the force x equals ma(x), or sum of the force y equals ma(y). Net force x component, or add them all up, equals ma(x). So let's find that acceleration first. Once I found that acceleration, I can say, oh, we'll isolate the 9 kilogram one, or maybe I'll isolate the 6 kilogram one, and we'll figure out what that force involved with that block is. Okay. Sum of the force x components. So that looks like the 13 comes in with a plus sign. The 8 comes in with a minus sign. These two have 0 x components, so they don't need to be written down there. And that's equal to the mass in the free body diagram times the resulting acceleration. So we now know the acceleration of the whole mess, which is the same as the acceleration of any of the 3 blocks as well. And that's good. I'm just going to say we've got that. Now, I want to find the force of the 6 on the 9. So I have a choice. That force is between these 2 blocks, and I might either say, let's draw a free body diagram for the 6 or the 9. Do you have any idea which one might be easier for me? Why the 6? And a normal force, and a force from the 9 on the 6. So we'll have 4 forces on this. I think its free body diagram will kind of look like this. It'll have 4 forces on it, right? There's one going to the left, the 9's pushing on it to the right, the plane is pushing up, and gravity's pulling down. So it will still have 4 forces. This one will have 4 forces too, right? It has the 6 pushing that way, it has the 2 pushing this way, it has the normal force and the weight force. But I still agree with Hala that this is the easier one. I just didn't hear the reason there. What's going to happen if I draw a free body diagram for the 9? Well, what forces are on the 9? Well, the 6 is pushing on the 9 in that direction. I might label that as just F6 on 9. And that's great. That's what I want. That's the answer to our problem. Unfortunately, the 2 is pushing in that direction. And I'm going to have a normal force and a weight force. But I have 2 unknowns. So if I do F net equals ma and use the A we know, to solve for this, I need to know this, and then I got to do another free body diagram. And I certainly don't want to do that on the exam if I don't have to. Right? So what happens with the 6? There's nothing wrong with this, but I'm just going to change my mind here and go with the 6. If I go with the 6, what forces are pushing on it horizontally and vertically? Well, it's got an 8 Newton force pushing to the left. It's got a force on the 6 from the 9. And it's got a normal force that I'm not even going to label and a weight force because we're only going to use the horizontal again. But those, it's important to put those in just to make it a complete free body diagram. Okay, so let's do for this one, the sum of the force x components equals max. This comes in with a plus sign, F on 6 by the 9. This one comes in with a minus sign in my axis, -8. This one's 0x component, 0x component. And then that is equal to the mass in the free body diagram times the resulting acceleration. And that is something that we know. So I'm just going to circle it. And that allows us to find F on 6 by 9. That's not what we were asked for. We wanted set F on 9 by 6. So how do I finish up here? Yeah. Do what? You can flip the sign. So again, when I put these variables here, right, I'm claiming, hey, I've got, in most cases, I know the force is in that direction. And so this symbol just represents how long that variable is. So when I solve for F6 on 9, that's telling me how strong is the force on the 6 by the 9. This isn't an x component that I'm finding out here. This is how strong that force is. I've already taken the component into account by putting a plus sign in front of it, right? This was an x component, but this symbol right here, this one and this one, are just how long those arrows are. And so when I find them out, I'm finding the strength of it. So I found the strength of F on 6 by 9. How does that relate to the force on the 9 by the 6? Just in terms of strengths. Their x components would be equal and opposite. That's Newton's third law. The strengths of the forces are exactly the same. So if I found the strength of this force, it's the same as the strength of that force. If I wanted x components, that's fine. We could give one a plus sign and one a minus sign. But I think your problem just wanted the magnet or the strength of the force, not a component of any sort. If they wanted a component, they'd have to give you axes for it to make sense. Is that enough on that one? Okay. What's next?
So that Newton's third law, is that why we ignore y in this scenario? Because like normal force is going to equal gravity? Or
Yeah, you know, so I would say no, Newton's third law doesn't have anything to do with ignoring y in this case. I'm ignoring y, or I could have said, let's take plus y to be up. I didn't even label it, but I could have done that. And then I could have done F net y equals may. Now I know ay is 0 because all the motion is along the horizontal direction. If ay were not 0, it'd be blasting off or burrowing into the ground. It's not doing that, right? It's moving horizontally. And so the only acceleration can be horizontal. And so ay is 0. So you're right. When I do F net y equals may, I'm going to get Fn minus 17 times 9.8 equals 0 because ay is 0. And that will tell me what Fn is. Now, this problem could have asked you for the normal force on all three objects or the normal force on one object, and that would have been a useful thing to do. But because we don't know the normal force and we don't want to know the normal force, there's no reason to put it in there.
One last question on this problem.
Yeah.
So then the force on 9 by 6, we're just going to switch the sign that we find for force on 6 by 9.
No, you don't have to, because both of these will be positive numbers. When I solve for this, I don't know what your ax is, but you know, notice it's going to be 6. Ax is positive. We're going to add 8 onto that. This will be a positive number. It is true that I think what you're saying is that if I did F on 6 by 9 x component, that would be the negative of F on 9 by 6 x component. That is Newton's third law. just respecting x components, right? It's saying, what is Newton's third law telling us about the interaction between these two objects? And what does that say about their x components? But when I label something on a free body diagram, notice, I just put 8 newtons here. Now, the x component of this force is -8. But I labeled it with an 8 because it's telling me how long that vector is. I already know which direction it's going because I drew the arrow that way, right? I don't need to worry about anything. So all these numbers here, you should think of as just the lengths of those vectors, right? Again, if I chose plus y is up, this force would have a negative y component, but I don't think of there as being a minus sign associated with it. It's just how strong is that gravitational force. Similarly, when I solve for this, that's telling me how strong that force is on the 6 from the 9, coming from this direction, how strong that force is. That's going to be equally strong as the force from the 9, 6 on the 9, right? Their x components will be different in my coordinate system, but the strengths of the forces will be the same. So I don't change the sign there. And the reason they're asking you for the strengths of the forces is they didn't want to give you a coordinate system. You still got to use a coordinate system to solve it, but they wanted to give you that freedom and say the answer is going to be the same in any case. So when you're drawing free body diagrams, these things that you draw next to it are just the lengths of the vectors that go in that direction. You've already thought about the directions of the vectors. So the lengths are just how strong that force is if you're talking about a force.
Got it.
Okay, good. Yes. Sure. Oh, okay. Yeah, this one looks super complicated, but we'll find out that it's not that complicated. Okay, so let me draw it. 21, 3, and then you can remind me what the acceleration is. The 21 is the one that's hanging, or the 3? Okay, so the picture kind of looks like this. You've got an inclined plane part, and then there's a drop off here, and then there's some kind of little pulley here, right? And we've got string going up there. And what did I say? 21 kilograms. And then this one's hanging off, and it's 3 kilograms. And we're told that the whole thing, you've let it go. And of course, it starts accelerating down. You're told the acceleration is what? Okay, so somebody's pushing up in this direction like that. 7.2. I know it's kind of getting small there, but I didn't leave enough room in there. Okay, so here's the secret to this problem. You'll find out, oh, it looks complicated up there. Just ignore all that stuff up there. I think are we asked for the tension in the string? Okay, so we want to know this tension. Wow, that thing, the whole thing is accelerating in the downward direction. We've got enough information to find the tension because look, we know if we call this plus y, right? I know all the y forces. I know the weight force. I know the upward force from the bottom. I know all the y forces except the one we want. That's the F net y. I also know AY. So I know both sides, and the only unknown is going to be T. So let's do the free body diagram over here just to clean it up a little bit. So I've got a 7.2 newtons going up in your version, right? That's someone pushing from the bottom on that. Of course, gravity is always going down. 3 times 9.8 mg is going down. And what about the tension? Is it going up or down on the 3? Tension force. So the string is actually pushing down on the 3 and forcing it to accelerate more and more. Now, a string can't generally do that, you know, unless it's really like stiff string or something. But no, where our strings only pull in this course. They can't push against things, right? That would be some hefty string. So the tension, so it's true. It's like someone's sort of lowering it down like that, but you're still pulling up at any point on it, just not pulling up hard enough to keep it from accelerating down. So the tension has no choice. It can only go up. And those are my three forces. Let's call plus y up, just for the sake of argument. And now let's do the sum of the force y components equals MAY. We've got three forces with y components. T plus 7.2 minus 3 times 9.8. The weight is the negative y component. That's equal to the mass in the free body diagram times the resulting acceleration y component. What's wrong if I do this and solve for t? Yeah, so plus y is up, it's accelerating down. So the acceleration y component has to be negative. You're right. If I put in a plus sign there, I'd be saying it's accelerating up, but we know the whole thing's dropping down. So I just ignored that complicated, the incline and all the stuff on the top. They just gave you enough information that you didn't need it. Yeah. The question was, when wouldn't we be able to ignore it? And I can give you an example of a problem. It's because we knew the acceleration. You know, normally the first thing we do is find the acceleration, and that involves all the pieces, right? If this mass up here is, is really massive, it has a lot of inertia, it might keep this, if there's a piece of styrofoam up here, this thing's practically going to be in free fall, right? It's almost going to be going down at 9.8. Whereas if this is really massive up there and it doesn't accelerate very fast down there, it's going to be holding this up and keeping it from accelerating very fast. So the acceleration is going to depend on it. And they just sort of short-circuited it in this problem. So let's do a simple example, and then I'll point to one that's more complicated. And if you really want to do it, we can do it. There might have been one like this in the homework. I can't remember. So here, frictionless surface, 10 kilograms, 3 kilograms, pulley, massless, frictionless pulley, right? Let it go. How fast does it accelerate? We could even throw a kinematics problem on the back, but let's just figure out what the acceleration is. Or better yet, let's figure out exactly what they asked for in the previous one. The tension. What's the tension there? If this is a massless, frictionless pulley, of course, it's the same tension up there we talked about. That's something you can always count on. Okay, so we said when we've got things connected by strings and they're not going in the same direction, we usually draw separate free body diagrams for the different objects. So here's my 3 down here. Tell me if I'm going too fast. The tension's pulling up on it, has no choice. String can't push down like that. And we've got a 3 times 9.8 going that way. And that's fine, except that I can't solve for t using F net equals ma because I don't know the acceleration yet, unlike that problem. Okay, but we could, undaunted. I know it's going to be accelerating in that way, so let me just, to make things somewhat easier, let's call this the plus x, or you call it plus y. Okay. And then I'm going to come over here to the 10, and it's got a tension going in that direction. Of course, I'm assuming this is frictionless because we're not talking about friction right now for this exam. And then I've got the weight force going down here. Okay. And then the last thing is, since I've chosen this as the positive x direction, I better choose this as the positive x direction so that we can use the same symbol for the acceleration x component, both those. Okay, and then we just do F net x equals max for both of those. Sum of the force x components equals max. In this one, the weight comes in with a plus sign, the tension comes in with a minus sign. The mass in the free body diagram is 3 kilograms, and we don't know the AX. So that's what I said. We want to find T, let's suppose, but I don't know AX. So let me just hold on to that. I'll half box it. It's not my final answer. And now let's do F net X equals MAX over here. 0x component, 0x component. So only the T, and it's going in the positive X direction. So all I've got on that side is a T. The mass in this free body diagram is 10. And AX is there. Again, I want T, but I don't know AX. But I've got now 2 equations and 2 unknowns. One of them is solved for T, so that's great, because if I substitute this for T in the other one, all my T's will be gone, and then I can find, no, we want T. I was forgetting what we wanted here. So I could say AX then is T over 10, and plug that in for AX over here. I've run out of room here, so let's go up here. 3 times 9.8 minus T is equal to 3 times, and now we know AX is T divided by 10. And I've just got to solve that for T. Okay, so let's see. We've got, so when I add, so here's a minus T, I'm going to add it onto the other side. We're going to have a plus T over there. So I've got 3/10 of T, that's 0.3. 3/10 is 0.3. 0.3 T's plus 1 T is 1.3 T's, right? Equals 3 times 9.8. And so I can solve for T. And then I, as usual, I'm being lazy, leaving out the units. I'm assuming everything's in SI units for my made up problem. So I just slap newtons on there when I solve for T, because a tension is a force, has force units. Okay, so that would be a case where I can't ignore what's going on up here. Now, if this were tilted up at a 30-degree angle, then things become a little bit more complicated, because this free body diagram looks the same, but this one now looks something like this. This thing's riding on an inclined plane, so I'm going to draw it like that. The weight force is still straight up and down. Oh, it's after 4. Okay, so let me just finish talking about this. The tension is pulling, we're going to presume, still parallel to the plane, so the tension would look like that. And the normal force goes up in this direction. So, we could still do things, right? And I would say to choose a consistent direction with this one, I would still take that to be the plus X direction. When I do F net X equals MAX, I still get a plus T on this side, but this force right down here, this one has 0x component, but this one no longer has a 0x component. So I've got to add on, it has a positive X component right there, right? Going from tail to tip, I'm moving in positive X. So I would have, in this more complicated problem, I'd have something else sitting there. Not too bad, but yeah. Yes, the magnitude of the acceleration is going to be the same, and that's because they have a piece of string between them that's not elastic, so it can't like get longer between them as time goes on. And that means if this one's moving to the left or to my left at 2 meters per second, this one's going down at 2 meters per second. The rate at which their velocities increase is the same, or their speeds increase. So
in order to solve for acceleration, like, it wouldn't matter necessarily if it was F or Y. Because
I'm not sure, are you just talking about, and you guys are welcome to leave if you want to, but I'll continue this discussion here. You're not talking about just changing this from X to Y, are you? Or you?
For like for the first free body diagram, you could write that to some of the forces for Y.
Yes.
Okay, and that would be fine.
I'm not sure what you're talking about. I could have relabeled this Y, and then my only thing I would have changed is that would go to a Y, which is sort of superficial, right? It's just a matter of whether I'm calling something left But yes, we want the direction each of them are going to be accelerating. We want to call that the same variable direction. So plus x or plus y, it doesn't really matter. Now, once I've chosen this as y, I could choose my x going up there, and then that would allow me to find the normal force too, if I really wanted to, if that was what was asked for in the problem. All right, good. If anybody wants to stay around for a couple more minutes, you're welcome to. Yeah.